Okay, a major category of chemical reactions is what we call redox reactions. Redox is a contraction of oxidation and reduction. So, let's start off with some terms. The first term, oxidation. So, oxidation is the loss of electrons, right? Or electron density. But for now, we're not going to talk so much about covalent compounds. Mainly we're focused on ionic compounds. So the loss of electrons. The result of losing electrons is that you see an increase in charge. Okay, so because electrons are negatively charged, if you lose your negatively charged electrons, you become a positive ion, right? When that happens, that is an example of oxidation. Now, the reason why the word is called oxidation is because historically it was first observed when metals reacted with air. And so when metals reacted with air, they gained oxygen atoms and became a compound, and so it was called oxidation because oxygen was joined to it. But they refined the definition later and said it doesn't really matter what's combining it, whether it's oxygen or sulfur or nitrogen. The point is the element has lost electrons. Right? So now, moving forward, oxidation is a loss of electrons. Okay, so the opposite of that is reduction, which is the gain of electrons. So if anything gains an electron, the charge decreases, it goes down. Right? So simple example, we'll do oxidation first. Sodium, if sodium loses an electron, it becomes Na positive. Right? The classic reduction, chlorine, if chlorine gains an electron, it becomes chloride, Cl-. So those are very, very common examples. Now, this must happen in pairs, right? Once one substance is oxidized, some other substance must be reduced. So what that's saying is both happen simultaneously. You can't have one. Anything else? You can't have one without the other. You can't borrow money if there's no one there to give you the money. Okay, so you can't have like a loaner. You can't have a loanee? Borrower. You can't have a borrower. Okay. So, the oxidizing agent is the substance which was reduced. Or in other words, the oxidizing agent caused something else to be oxidized. The reducing agent is the substance which was oxidized. I know this is kind of confusing, but this makes more sense when you look at it in terms of reactions. So let's look at this first example here. Okay, so here's sodium reacting with chlorine to form NaCl. So in NaCl, if I asked you to look up the charge of sodium and chlorine, you'd be able to look up to your chart sheet, or you would just know that sodium is positive and chlorine is minus. Okay, so let's track these. The sodium went from being alone, and anytime an element is alone, if there's no charge written next to it, there's no charge. That means the charge is zero. So what happened to chlorine's charge from beginning to end? It went up. Therefore, sodium was oxidized. Chlorine's charge at the beginning is 0. But as we see, it went and became negative. So chlorine's charge went down. Chlorine was reduced. So the element that was oxidized caused the other element to be reduced. So what's being oxidized? We already said, well, it's sodium. What's being reduced? Chlorine. What is the oxidizing agent? Chlorine. What is the reducing agent? Sodium. So in other words, you can't both be oxidized and be the cause for oxidation. Does that make sense? If you're oxidized, then you're the agent of the reduction. If you're reduced, you are the agent of oxidation. Okay. This reaction is split up into two half reactions. If you look closely, this reaction and this reaction, if I added them together algebraically, I would end up getting this. All right, but we're going to go through half reactions in just a little bit. Let's do some other examples first. Magnesium will react with hydrochloric acid, HCl, forming hydrogen. Now, they only gave me one product. What do you suppose the other product is going to be? Yeah. Well, we balance it. Let's put a 2 there. Okay. The hydrogen can then be burned in oxygen to generate water. Okay, so I didn't give us enough space here. Hydrogen burned in oxygen to form water. Okay, so these are the two main reactions. Let's write half reactions for both. Okay, the half reaction shows the element undergoing its change in oxidation number, the one that's being oxidized and the one that's being reduced. So here's really what we're looking at here. So if I write these half reactions, the first one looks like this. Mg goes to Mg positive 2. Now, all equations must be balanced, including the charge. So in this simple equation right here, if the charge on the left is neutral and the charge on the right is positive 2, we've got to balance it by adding 2 electrons to this side. Okay, let's do the other one. H plus becomes H2. Well, first, I need to balance the number, so I put a coefficient of 2 there. But again, charge must be balanced, so the left side is missing 2 electrons. And I don't need to include chloride in these half reactions because chloride's charge did not change in this process. Chloride is known as a what? It's a spectator ion, right? Nothing happened to it, so it's we kind of ignore it. Okay, let's look at the second reaction here. So if oxygen here, O2, is all alone, what is its charge to start with? Yes. In the compound of water, what would the oxygen charge be? -2. All right. Hydrogen is all alone at the beginning. It's going to have a charge of 0. In the compound of water, hydrogen's charge is what? +1. Now, there are 2 of them, but when we write charges, we always write the charge per atom. So I know there's 2 hydrogens here, right? But that +1 means per hydrogen, okay? All right, so half reactions. We've got H2 going to, we have 2 hydrogen ions in water, so we put the 2 in front, and we'll have to add the electrons to balance that. Oh, actually, I didn't balance this. Let's go back here. We have to balance this. Put a 2 there, which means this is not a 2, this is a 4. So this is a 2 here, that's a 4, and that's a 4. Okay, for the oxygen, O2 goes to 2 oxygen atoms in the compound, so the only way to balance that would be to put 4 electrons here. Okay, what was oxidized? Yeah. What was being reduced was oxygen, so therefore That's the oxidizing agent. The reducing agent would then be hydrogen. Okay, I know I kind of glossed over where we got these charges from, but remember, for now, you can just use the charges from your chart sheet, right? If you forget what a charge is, just look it up. Okay, new term. New term, kind of, not really. Oxidation number is simply the number that we were calling charge all along. Right? So it's the charge an atom would have. Its electrons were completely transferred to the more electronegative element. Right? So we know it as charge. In any redox reaction, we expect changes in oxidation number because since whenever electrons are removed, charges will change. Now, in a compound, we need to be able to evaluate a compound, and we need to assign oxidation numbers, and there are 6 rules. And I know there's 6 rules. It seems like, oh man, more rules to remember. But to be honest, these are kind of like common sense, right? So it's really not as many rules as you think. Okay, so let's go through them. The first rule says, any free element has an oxidation number or a charge of 0. And that's literally when I said, like, H2, right? If it's all alone, right, it's not bonded. If it's not bonded, its charge, its oxidation number is 0. Okay, anytime you see an equation, something's unbonded, its oxidation number is 0. Rule 2. The oxidation number for any simple ion is equal to that charge. So if the equation showed like Cl minus, well, the oxidation number on chlorine would be -1. That's what we mean by simple monoatomic ion, meaning an ion made up of one atom. Like F minus would be -1, right? S minus 2 would be -2. Ca plus 2 would be oxidation number +2. So simple ions are very straightforward. The oxidation number simply is the charge. Rule 3. The sum of all oxidation numbers on all atoms in a molecule or ion must equal the overall charge. Okay, so remember polyatomic ions? Let's start simple. Hydroxide. You know that hydroxide carries a charge of -1. Well, what are the actual oxidation numbers on both elements? Well, in hydroxide, oxygen is -2 and hydrogen is +1. So when you take the sum of those, that's how you get an overall charge of -1. Let's do another example. NO3 minus. This is nitrate. So the overall charge is -1. But we have 2 elements. We've got the nitrogen, and you got 3 oxygens. Now, oxygen's charge is -2. So if I have 3 oxygens, each carrying -2, plus a +5 from nitrogen, that makes sense that my overall polyatomic ion's charge is -1. So do you guys see what I mean? Like, this is a rule, but it's kind of common sense. So it's not really something you have to commit to memory. You just have to know that if it's a polyatomic ion, you can dissect the atoms, and you can look at the individual oxidation numbers on each of the atoms. Okay. Rule 4. Fluorine has an oxidation number of -1. And you might think, well, that's kind of silly. Why do we have a rule just for fluorine? Well, remember how fluorine, I've mentioned this a couple times, fluorine does its own thing. Like if I asked you to rattle off the list of strong acids, you would say HCl, HBr, HI, but you would not include HF, right? Fluorine is a special case. There's a lot going on with fluorine. And so part of that is that it has its own rule. It has an oxidation number of -1 because whenever it's in a compound, fluorine will always be the element that is able to take an electron towards itself. Because, as we'll discuss later, it has the highest electronegativity. Nothing else beats fluorine when it comes to taking electrons. Okay, so it's a rule. And it's actually not even that important because you don't see fluorine very often. Okay, rule 5. Hydrogen and other alkali metals have an oxidation number of +1. But was that really a rule? You already knew that alkali metals are all +1. We mentioned that when we talked about formulas and naming. Okay. Earth metals have an oxidation number of +2. You kind of already knew that as well. But this is new. Hydrogen can be -1 in hydrides. Okay, a hydride is when hydrogen bonds to metals. So hydrogen we typically think of as +1, but when hydrogen bonds to a metal, the metal will pretty much always be positive. You cannot have a negative metal ion, so that means hydrogen takes the electron towards itself, and it's the negative one. Okay, and then the last rule, oxygen will have an oxidation number of -2 when it's in compounds. Now, little caveat here at the end, when rules conflict, follow the rule that's lower in number. Okay, so the lower the rule, the more important, lower number of the rule, the more important the rule is. Okay, so the point of this, when you actually see this, is rule 5 is more important than rule 6. So, example. This is hydrogen peroxide, H2O2. So if I said, let's assign oxidation numbers to these elements, rule 5 says that each oxygen is -2, and there's 2 of them. I'm sorry, that's rule 6. I said it back. Rule 6 says oxygen is -2. Rule 5 says hydrogen is +1. But if you look at this math, this does not compute. 2 minus 4 does not equal 0. So that means both of these rules cannot be followed simultaneously. That means the rule lower in number is more important. And the rule lower in number means the hydrogen rule is more important than the oxygen. So that means oxygen cannot be -2. Actually, in peroxides, oxygen is actually -1. And if I'm honest, this is probably the only time you see this, where there is kind of a conflict, is in peroxides. So other than that, it's not really going to be an issue. But I'm just saying it now so that you are aware of it. Okay. So yes, there are 6 rules, but as we go through this process, you will see that it's not necessary to commit these to memory as long as you have practiced these a couple of times. So let's do this first example here. HPO4 with a -2 charge. Let's find the oxidation state in each element. All right, so first, hydrogen. Hydrogen is +1 because there's a rule that says hydrogen is +1. Rule 6 says oxygen is -2 because that's a rule. So what do we have? We've got +1 plus, we don't have a rule for oxygen, or for phosphorus, sorry. So we'll call phosphorus X. Plus 4 times -2, and this has to equal -2 overall because it's a polyatomic ion and the total charge is -2. So this is how we will deduce what the other element's oxidation number is by figuring it out by difference. All right, so we get +1 plus X -8 is equal to -2. Right, so X minus 7 is equal to -2. So +7 to both sides. X is equal to 5. You don't have to do all that work. I'm just laying it out as an example. Let's try K2Cr2O7. Now this is a neutral compound, so everything must be zero sum. So I've got potassium. What's the charge for potassium? +1. It's an alkali. So we got 2 times +1. Chromium we don't know. So we'll have to figure that out because there's no rule for it. Oxygen, the rule says that it's -2. So what do we have? We got 2 plus 2x minus 14 is equal to 0, which means 2x minus 12 is equal to 0, which means 2x equals 12, which means x is 6. Chromium's charge is 6. How are we doing so far, guys? Okay. You ever have that friend who acts one way with you, but then like in a different crowd acts like someone else? You barely know the person, right? And then this person like will go with another group, and then like you don't even recognize who that person is. So nitrogen is that friend. Nitrogen is nuts. Like let's go through and let's follow the rules and let's assign oxidation numbers to nitrogen. So, okay, we have a rule for oxygen. Since you know oxygen is -2, in this first compound, what will nitrogen be? +2. Okay, let's go to the second compound. Look, there's 2 oxygens, so 2 times -2. What does that mean nitrogen is here? It's going to be +4. Okay, so 2 times nitrogen plus 5 times oxygen. So -10 is countered by 2 times x. The charge on nitrogen here is what? It's got to be 5, right? You see what I mean? Nitrogen is all over the map, right? Clinically schizophrenic. Could be a sociopath, right? -2 times 3 plus 3 times what nitrogen is. What's nitrogen here? Plus, oh, I put the wrong number there. Hold on, that's a 2 in front. Right, +3. How about ammonia? What's ammonia here, Nick? That's going to be -3. Hydrogen is +1, so -3 on nitrogen. Okay, so you get the point here. There are some elements that are like chameleons. Okay, whenever we come up with a set of rules, the set of rules is designed to satisfy the majority of conditions, the majority of the situations, right? And so if an element is left off out of this rule, that means that's probably the element you'll have to figure out by the end. That's the one you do last. It's the one you figure out by difference. Okay. So take a second, look at this reaction here, HCl plus HNO3. Try to figure out what element is oxidized, what element is reduced. And again, you got to do that by looking up charges. the easiest way is to start with the hydrogens and oxygens. And usually the rest kind of like fall into place after you do those. All right, so I guess let's start by assigning oxidation numbers. We're going to go from left to right. What's hydrogen? +1. So that would make chlorine. -1. Okay. Hydrogen again. +1. Oxygen. -2. So what would nitrogen be here then? 5. Okay. All right. Products. Oxygen is -2 each. Remember, again, you only write the charge per atom. Okay, yes, I recognize there's 2 of them. What is oxidation number of nitrogen then? 4, correct. All right. Coefficient of 1/2 does not change what the charge is. The fact is this chlorine is all alone, so it's 0. And then in water, +1 and -2. Okay, so now we look and see what element had its charge go up. Yeah. Chlorine. Okay, so that is our oxidation. What element had its charge go down? Nitrogen. So this is your approach for identifying what element was oxidized, what element was reduced. Now, just to be clear, not all reactions are redox reactions. Metathesis reactions are not redox. That's why it's a different category. So the ones we did on the board, the double replacements, all of the charges stay exactly the same. Right? No electrons are exchanged, so those are not redox reactions. So redox reactions are only when the charges actually change. Okay. Okay, I'm going to pause this here. What I want us to do is